Okay. Hopefully everything is working. I ran into a lot of tech issues. So I'm sorry for the delay. But yeah, once again, if my stream cuts out or if like anything happens, please tell me in the chat. It shouldn't cut out. I did a more messing around with the settings and whatnot, but hopefully that fixes it. I still don't really know what's wrong. I also had issues with my thing that helps me multi-stream, so my restream is also having issues today. But that's okay, I figured a way around it. But yes, I'm having a lot of tech issues, so if the stream cuts out and I didn't say bye yet, it probably means that it was unintentional and that it was either my internet, my software, or something else that happened. So please tell me in the chat. And sorry for the delay, so I won't keep yapping for much longer. And let's continue to learn physics, shall we? So I'm going to go over a super quick review of what we learned last time, which was scalars and vectors. So a scalar has like a sort of like single quantity, while a vector has sort of like two pieces of information. So a vector has a magnitude, which is like the number or how much of something, I guess, and then the direction. And a vector has a tail and a head. Then it can measure displacement and like the direction and how far that direction or the displacement is. And then we also have like operations. So we can check if they're like parallel, and they have like, it's sort of like equations. Hi, sorry, I need to stay lurking. Hey, no worries. Thank you for saying hello, and thank you for the lurk. Hopefully my bot is working. If it's not working, well then I'm screwed, because nothing is working today. Oh no. Bot. Oh no, it is, huh? Okay, well, I don't know. Today's a mess. I don't know why my lurking command isn't working. Well, that's interesting. Well, to continue, so you can have like, you can multiply and things like that. So let's say we have the negative flips the direction. So when we want to calculate something like a negative b, so we have a and b here. If we want to add them, you have the two tails next to each other, and then you sort of create like a line. You create like a connection between the two, and then you can create this vector, and this vector is the sum of the a and b. And for the negative, you can simply rotate the b like 180, just flip it, so that's facing the complete opposite direction. And then you can do the same where you can draw this line and you get the resultant vector of the subtraction of both. But yeah, that's where we are. What else? Okay, we're on 2.2, so this is the coordinate systems and components of vectors. So this chapter is actually quite long, or this section is quite long, so hopefully we can get through all of it. If not, there will always be next time, but I think we can. We'll see. Hopefully my voice lasts long enough. Alright. Sorry, I didn't write the title because I was in such a like mess with the whole tech issues. I hate tech issues. But I hope you like the little drawing I made. Speaking of drawings, I think next Thursday I'm gonna have a like help me design a mascot for our strawberries, our little community group. And my art will be horrible, but I will commission someone to actually draw it properly. And please ignore my horrible handwriting. I am really bad at writing on a tablet. I'm not used to it. I like to say I have all my notes retro style, because I still use an old pen and paper. even for like school. The amount of people that I see that have switched over to tablets in the past few years has been a lot. When I first started like college, I would say it was around like half and half. Half of them would use tablets and the other half would use like paper and pen. But now it's like 90 or like 80% of them use tablets. So that's always interesting. All right, I shall begin reading. Learning objectives. By the end of this section, you will be able to describe vectors in 2 and 3 dimensions in terms of their components, using unit vectors along the axes. Distinguish between the vector components of a vector and the scalar components of a vector. Explain how the magnitude of a vector is defined in terms of the components of a vector. Identify the direction angle of a vector in a plane. Explain the connection between polar coordinates and Cartesian coordinates in a plane. Vectors are usually described in terms of their components in a coordinate system. Even in everyday life, we naturally invoke the concept of orthogonal projections in a rectangular coordinate system. So, orthogonal projections in a rectangular coordinate system just means like, it's like perpendicular, I think, right? Perpendicular projections. I don't know why, I mean, they're using a much more, they use different words for, like, that mean the same thing. But orthogonal just means perpendicular, if I'm correct. For example, if you ask someone for directions to a particular location, you will likely be told to go 40 kilometers east and 30 kilometers north, then 50 kilometers in the direction 37 degrees north of east. In a regular Cartesian xy coordinate system in a plane, a point in the plane is described by a pair of coordinates x and y. In a similar fashion, a vector A in a plane is described by a pair of its vector coordinates. The x-coordinate of vector A is called its x-component, and the y-coordinate of vector A is called its y-component. The vector A component, or the vector x component, is a vector denoted by A. The vector y component is a vector denoted by AY. In the Cartesian system, x and y vector components of a vector are the orthogonal projections of this vector onto the x and y axes respectively. In this way, following the parallelogram rule for the vector addition, so that's what we talked about earlier with the whole like connecting the two tails together and then drawing lines to create a parallelogram, then you get the resulting vector. Following the parallelogram rule for the vector addition, each vector on the Cartesian plane can be expressed as a vector sum of its vector components. Alright, so that's a lot of information right there. Good afternoon. Hello, good afternoon. So, we can write down that there, for an xy coordinate system, let me do this. Yes, I can use the back button. I'm just gonna call it chord system. Or chord sys. Like that. For xy coordinate system, there is x and y, and then we'll circle the x and y maybe in a like slightly different color. There's an x, and there's of course the y component. And then for vectors, so vector A has two, well, it can be described by, vector A can be described by vector coordinates. Can be described, how do I spell described? Described by vector chord. Chords. I'm just gonna call it chords. Will it be okay if I miss lecture 1 and 2 for this class? No! How dare you? How dare you miss my class? That's horrible. Alright, straight to the pit. We're gonna stick you in a vacuum chamber. Yes, it should. That being said, it's totally fine. Like, I definitely do think you should be, like, I think you can still be able to understand what I'm trying to get at. Hopefully, I did a good enough review, but the main part of the previous lecture was just like the addition and subtraction. So it's the parallelogram rule. So like the whole, you got like the two tails, you draw lines from them, and then you can get a resultant vector. Or if it's like negative, you just flip it. I think that was the main takeaway of the previous lecture. And then the lecture before that was whether or not a value was reasonable and estimation. So I guess once you know sort of numbers where you can like reference something. So like a car, if you let's say you calculate a car. The car should not be going 1 billion miles per hour or 1 billion kilometers per second. So yeah. Yeah, if you miss another one, I might have to throw you in the vacuum chamber. Yes, I think hopefully I with the reviews and stuff, hopefully anyone who just joins can be able to at least like understand something from this. But yeah, main point of last time was just the parallelogram rule for the addition subtraction. And then I guess this one we'll talk about how there are like x and y components of a coordinate system, or I guess xyz when we get to the 3-dimension one. So, and then we can put and we can have the a and the y. So the a vector has 2 components. So two vector components to describe the a vector. 2x, or I should say has a has x and y components. And also these components are also perpendicular, and I'm going to use this symbol to denote that it's perpendicular, or in this case, as they describe in the textbook, orthogonal. But yeah, that's pretty much it. Oh, and also the whole like the sum will equal the total a vector. There we go. Okay. As illustrated in figure 2.16, vector A is the diagonal of the vector where the x component, ax, is the side parallel to the x-axis, and the y component, so ay, is parallel to the x-axis. Vector component ax is orthogonal to the vector component ay. So here we have this sort of like axes. We got your x down here. Can you see my cursor? No, you can't. Okay, now you can. There we go. So here we have the y component, or sorry, the y like axes, and then we have the y component of the a vector, which is parallel to that y. Then we have the a component of the a vector, which is parallel to this x-axis. So maybe I can like recreate that in the notes. I'll have. Oh my gosh! Hello, and thank you for the sub. That scared me a little, not gonna lie. Alright, so let me draw the X. I'm just gonna draw it very small because I don't really have, well, actually I have kind of unlimited room, but for the sake of trying to make everything look the same, we can have that. That will be your A, Y. By the way, thank you for the sub and welcome to the welcome to the strawberries. Welcome to the strawberry communities. The strawberry community. There we go. Okay, so we have that, and then we have the full A vector, which I will give it a nice purple color. And if you draw like a line, so just like sort of imagine a line that goes here, we'll have like, okay, they're supposed to be straight lines. just imagine them, that they are straight lines. Okay, there we go. Yeah, okay. It is customary to denote the positive direction on the x-axis by the vector I, and the positive direction on the y-axis by the vector j. Okay. Using unit vectors of the axes I and j, define two orthogonal directions in the plane. As shown in figure 2.16, the x and y components of a vector can now be written in terms of the vector units of the axes. This. The vectors a x and a y define that equation and are the vector components of vector A. The numbers ax and ay that define the vector components in this equation are the scalar components of vector A. Combining the two equations, we can obtain the component form of a vector. So that was a lot. That was a lot to take in. Let me scroll down. How do I do this? Right, I can... Okay. I forgot how to use the whiteboard. Okay. Go back. So, what can we take from this? We can take that the x-axis by the unit vector I. Positive direction, so we'll put plus as positive. Positive direction on x n on x axis by the unit vector I. So we'll just put as I, and then we'll give it I hat, a little hat. 'Cause I can't bold my writing, so this denotes that it's like a vector, and the little hat also. And then we also have plus direction on y is j. As a person who really struggles with telling the difference between letters, I hate how it's like I and J. They look the same. They're too close to each other, and I don't know who decided to do that, but I don't like you. Define two orthogonal, so the unit vectors of the axes define two orthogonal directions on the plane. So here we have that. So I guess the I and the J's define the directions. Maybe I'll use a different color. Orange? Let's use orange. So we'll say that, like, this sort of defines the axes of it. We'll have, like, this. Then I. Then little hat. Oops. The hat. And we also have like this way. AX. And then we have a little hat of I. So basically, this sort of tells you whether it's positive or negative, I think, in the direction. And it tells you, like, oh, this is the direction. But this is like the sum of... This is still the A vector, which is like the sum of them both. And then if I go back to here, I feel like 2.11 is a good equation to note. So I can never write these brackets correctly. They always end up looking kind of funny. AX I Y, and we have a Y, and then the J with the hat. So the numbers AX and AY define the vector components. So if you notice, one thing to like really note is that, okay, thank you. Thank you, whiteboard, for your new features. That you see how this is a vector in this case? We have like the little vector symbol like the arrow. In this case, AX does not have that arrow, so that implies that it is a scalar component, which means it holds one piece of information, while the I and J hold the piece of information of like that direction. So this holds that magnitude, and then the I and J hold that direction information. All right. And then we can get the total vector by, once again, sort of combining both of these equations. We can get the total A is equal to AX I plus Y J, and we have a little hat. No, I didn't mean to click that. Okay. We know the coordinates B, X, B, and B, Y, B of the origin point of a vector, where B stands for beginning, and the coordinates for E, X, E, and E, Y, E, the end point of a vector, where E stands for the end. We can obtain the scalar components of a vector simply by subtracting the origin point coordinates from the point coordinates. So if you take the... Oh, okay, I see what they're saying. So once you get like this sort of value of the A and Y components, once you take that like length at the start and at the end of your vector, so let's say we want that magnitude, so we can take the... Can I do this? Okay, so let's say we want the magnitude of this AX vector. We can find that value at the point here, and that value at the end here. So once we subtract that, we can get that scalar magnitude value. So we have... I kind of want to write it like this, and Y, oh, no, YB. So basically XB and YB represent the point, or like the value where the vector begins. Where vector begins, B begins. There's two N's, begins. Begins. Yes, I think there's only one N when it's just begins. Where the vector begins, for each the xy component. So for each x and y component. And then same with the other one. Same with xe and ye. Let's make the e a little smaller. E where vector ends. Vector ends. Yeah. Okay, let me move this down so that my giant head does not block. Let me zoom out a little as well so you can make sure that I'm moving this properly. And then I'll zoom back in. There we go. Hello, first time seeing your stream. This reminds me of something I saw in YA. Perelman's Physics for Entertainment version 2. I never heard of that, but I hope that means a good thing. I hope, at least, like, I hope it's a good thing. Alright, example. So we get an example. Displacement of a mouse pointer. A mouse pointer on the display monitor of a computer at its initial position is at the point 6 centimeters and 1.6 centimeters with respect to the lower left corner. If you move the pointer to an icon placed at point 2.0 and 4.6, what is the displacement of the vector? So, I guess we're just gonna use what we just learned, which is, like, you subtract the two? But let's see what strategy they say, and let's go through the example with the book. The origin of the XY coordinate system is the lower left side corner of the computer monitor. Therefore, the unit vector I on the x-axis points horizontally to the right, and the unit vector j on the y-axis points vertically upward. The origin of the displacement vector is located at point B6, 16 at the end, and the end of the displacement vector is located at E2 and 4.5. Substitute the coordinates of these points into that equation that we had above here, and find the scalar components dx and dy of the displacement vector d. Finally, substitute the coordinates into equation, the one above, with the like I and j components, to write the displacement vector in the vector component form. Okay, so I think I missed something important. By that I mean I should specifically say that this is the vector component form. Component form. What other physics topics does your engineering courses go over? Well, I actually finished all my physics, but I must admit I was quite horrible at physics, specifically kinematics. But I'm going to be basically going, hopefully one day, I will finish this entire textbook, and I think this is like the first semester of university physics, but I'll be going over it slowly and with like no pressure, because I think people learn the best that way, or at least that's how I learn the best that way, is when there's like no pressure and I can finally go at my own pace. But so I'm in chapter 2, which is basically all vectors, but eventually we will get through all of kinematics. And there's also like 3 editions of this book, so it continues all the way through. But yeah, for now it's just gonna be vectors, and like I think the next section is vector algebra, but I usually go one section at a time depending how long the sections are, as well as how long I can keep talking. Oftentimes my voice will give out in like my voice sort of like starts to fade at 2 hours, and that's when I'm like, okay, I can't speak anymore. But yeah, I also used to do a little bit of coding as well, and I kind of want to get to code a bit more and stuff. But for that one, I think I prefer to do that in the form of games. I know there's a lot of coding games, or like there's a lot of logic games. I actually have one. I haven't played it yet because I have a billion games on my Steam that I need to finish. Like, yeah, one of them that I want to play is called Hacknet. I honestly am gonna go into that game completely blind once I get to it. But yeah, that's what I usually do. And occasionally I always have like videos of PowerPoints. Although in terms of project-wise, that's been put on pause for a little bit of time because I want to work on some other things first. All right, so should I write down this example? Sure. So basically, an example, I should probably make that a different color. Let's make it like green. I used to make it green, I think. So we have example 2.3. We have start. So let's like gather first the most important information. So we have the start points at 6 and 1.6. I am not going to write the units. You definitely should write the units, but I am embarrassed with my penmanship, to be honest. And any writing that I can write less of would probably be better. All right. So basically, we want to find the displacement, so we have the starts and the ends. So we can have dx, which would be this and this. Then we have the end, which is 2, subtracted by 6. Of course, we get -4. And here is where I add the units. Although, if you're a person who is forgetful, which is, I guess, me, I should be adding the units. 4.5 and 1.6. I don't have a calculator with me right now, but I trust the book and okay, yeah, this is correct. Or I can just do mental math. It's not that hard in this case. Not hard yet. And then we can put it into this vector component form up here. So now that we have the scalar or like the scalar displacement value of each. So to do that, we put this. That's looks horrible. There we go. This is better. We got -4 I plus 2.9 j hat. And they should all have centimeters for the units. But yeah, okay. And then here we have the graphical representation of that, where we have the negative d, which is going to the left because that's negative, and we have the positive d, which is going up. We can do the parallelogram rule, so we can add the both. Then we get this as a resultant. And yeah, so basically it's like the distance. So this is your distance and it's going this direction. Then you can make sure like the tails are connected to each other. So we do the parallelogram rule and then we get the final vector. Significance. Notice that the physical limit here, 1 centimeter, can be placed either with one component immediately before the unit vector or globally for both components, as in equation 2.14. Often, the latter way is more convenient because it is simpler. The vector x component, dx, is equal to the -4 I hat of the displacement vector as the magnitude. So the magnitude is when we absolute value both. It equals 4 because the magnitude of the vector is because the magnitude of the unit vector is 1. The unit vector I is 1. Wow, I can't read. Notice that the direction of the x component, is negative I hat, which is anti-parallel to the direction of the x-axis. Hence, the x component, vector dx, points to the left. So because we get a negative here from like that displacement, so we get that like -4, the x component, which is denoted as the I hat, is in the anti-parallel direction of the x, which basically means it's going the other way. The scalar x component of vector d is dx is equal to -4. Similarly, the vector y component, so dy, is equal to 2.9. J hat is the displacement. Displacement vector has magnitude of 2.9 because the unit vector j absolute value is equal to 1. The direction is positive, which is parallel to the direction of the y-axis. Therefore, the y component, vector d, points up. As seen in figure 2.17, the scalar y component of vector d is dy is equal to plus 2.9. The displacement vector d is resultant of its two vector components. So I guess all of this like significance paragraph is saying that once you're basically finding like the distance between the two as well as the direction, and you can denote it by this vector component form, and then to find that distance of each component of that change of like basically like this coordinate system, to find that difference, you can get you just subtract it and then you get a value. And note that the negatives and positive do mean whether or not something is parallel or anti-parallel to the x and y in this case, because we are in the xy coordinate system. But yeah, that's what that is saying. What else? Vector component form of this displacement vector tells us the mouse pointer has been moved on the monitor 4 centimeters to the left and 2.9 centimeters upwards towards its initial position. In my place, we call it J cap. Oh, cap. I've always heard it as hat. Maybe it is cap, and maybe I heard it wrong. But to be fair, a cap is a type of hat, right? So it's still hat. It's just a specific type of hat. Let me move it up so that my big head doesn't block the notes. Oh boy, my voice is starting to go. It's fine. A blue fly lands on a sheet of graph paper at a point located 10 centimeters to the right of its left edge and 8 centimeters above its bottom edge, and walks slowly to a point located 5 centimeters from the left edge and 5 centimeters from the bottom edge. Choose a rectangular coordinate system with the origin at the left side corner of the paper and find the displacement of the vector. Illustrate my solution by graphing. Let's try this. Let's try this out. So I guess this is another example, but they don't tell us the solution. That's okay. I could be wrong, so please take what I do as a grain of salt. I call myself a failed engineer for a reason. And I'm honestly still learning this myself in many ways. Like, yeah, I took a class on it, but that doesn't mean I did too well. Check by understanding 4.2. So, we have a fly. A sheet of graph paper. Okay. So let's draw like a little paper first. Why? What is going on with my... Okay, I didn't know whiteboard had. So basically, like, the whiteboard thing that I use to write all my notes and stuff like this, it, like, had an update, and now I kind of don't understand how a lot of this thing works. But yeah. If you're a failed engineer, what's your major now? So, I call myself a failed engineer. I didn't drop out or anything, you know, I just feel like a failure. But yeah, I'm still an engineer, unfortunately. But we learn by failures. That's true. Have I failed some classes? You know, maybe. But I've not failed out. I've not dropped out. What are they asking for? What do you mean, what are we asking for? We're gonna do this example, if that's what you mean. We are on page 58, if you'd like to follow along. By the way, the book is like open source and it's free. So if you want to go at a much faster pace than I do, or just like even check out the other books, this website is basically all like open source. You don't need to, you get like tons and tons of good information and good access to good textbooks for no cost at all. But yeah. Yo, Conjurer, hello! Hello. How have you been? I wanted to see like one of your Warhammer streams, but I missed it. Because I can't wake up early. I have problems. I have a lot of problems. I saw like, it's been so long, but I like popped in and I saw that you had like a chibi, like you have a chibi model now. And it's adorable. And I can't believe I missed your chibi model. I can't believe I missed your chibi model debut. It's been so long. I really need to like fix my sleep schedule so I can finally watch you like while you're streaming. All right. So blue fly. Maybe you should make that fly blue. Lands on a sheet of paper located to the right of its left edge. And so like let's just say here it lands here. So this coordinate right now is 8 centimeters. But yeah. And above its edge, then walk slowly to a point located 5 centimeters from the left edge and 5 centimeters from the bottom edge. So it gets even... Okay. Well, that's unfortunate because I wrote it where it should be. I'm gonna write it out here. Okay, why am I writing in the decimals when I don't have space for them? Move here and walk slowly to a point located 5 centimeters from the left edge. So like here and 5 centimeters from the bottom. So like here. So it's like at position 5-5. That's a 5, that's not an S. There we go. Choose rectangular coordinate system with the origin on the lower left corner of the paper and find the displacement vector of the fly. So we have like the start and end. Okay. We kind of do the same thing that we did previously. Oh, if you want to watch the debut, I have a highlight video. Okay. That's good. I will definitely check that out. What does displacement vector mean? Like from 10-8 to 5-5. Yeah, so that is like the vector, so that is the direction and the magnitude of change from the 2 points. Basically, if you go from one area to another, that like displacement is, the displacement vector would be like this vector that, you know, it got displaced. And then they want us to show it in like this form, I think, so we can get each like the x and y components of each. So let me switch back to green. So -5 and -3. Yes, 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 exactly. Oh, oops. I wrote it backwards. It should be like this. So -5. I'm gonna write the centimeters now. Make sure to write your units. Don't be like me, don't be lazy. Do as I say, not as I do. We have 3 centimeters. Let me get that. And then we can write the sort of full displacement vector in its vector component form with the -5, I hat with a -3, the j hat, and we can get the centimeters. So then we have like this. I should have really gave myself more space for this, but I didn't, and that's okay. So we have that as dy. Is my head blocking? No. Okay, my ginormous head is not blocking. I wrote it backwards again. Negative, and this... No. Okay, thank you. I want to... This should be the other way around. I'm so sorry. 8. Thank you for catching my mistakes. Like that. So we have it in both, like, the anti-parallel directions of the, by the way, y and x. But yeah, I should have gave myself more space, but then we have the, like, resultant vector here as d. But I think that's what it is. Why are you doing them apart? Is that how you were taught? Well, that's how the book does it. I guess I was taught like this. I don't really remember. It's been a really long time since I've actually taken a physics course. But the book does it like this so since we're using this book, I guess we'll do it like this. Of course, there are definitely like tricks. You can probably just like subtract it. You don't need to write it out entirely, but for the sake of the understanding and of this, of like keeping it as similar as the book so that the notation is not all confused and stuff, I'm gonna continue to write it like this. Also, like, it explains it step by step, so I guess that's a good thing. So next section. When we know the scalar component ax and ay of a vector a, we find its magnitude a and its direction, I guess theta a. The direction angle, or direction for short, is the angle the vector forms with the positive direction on the x-axis. I see your chats. I'm not ignoring them. I just want to finish this section, this like small little section first. The theta a is measured in the counterclockwise direction from the ax to the vector, shown in figure... What? 2.18? Where? It's figure 1.7. Oh, down here. I'm so stupid. Okay, the direction is shown in this figure down here because the lengths a, so the ax component and the ay component, form a right triangle. They are related to the Pythagorean theorem, which is, you know, the a squared plus b squared equals c squared, but in this case it's ax squared and ay squared. This equation works even if the scalar component of a vector are negative. Scalar components of a vector are negative. The direction, theta a, of a vector is defined via the tangent line of the theta a on the triangle shown. So back to geometry. Alright, are you studying for an exam or just learning because I enjoy it? For now, I'm just learning because I enjoy it. I've actually taken all my exams related to this stuff. I didn't do too well, but I scored... Well, so this is like a common thing in physics, like engineering engineering physics, oftentimes like the average score is like so horrible that the professor will need to curve it, or else he will end up failing like 90% of the students. But yes, long story short, I did horrible, but so did my class. I've retrieved my copy of the book. Is a author presenting the basics of physics. Oh, in an entertaining way. Oh, I see. I have the 1972 printing in English. Parallel Man. So is it like a fun sort of book? Like, is it supposed to be so you said it's like an entertaining textbook. That's very interesting. Wow, I do not miss this. For me, I actually hated physics to begin with, but as I got more into the computer side of things, I'm like, okay, take me back to physics, please. I'm quite horrible at coding. That's okay. Luckily for me, now my focus is sort of more on the physics end, which is okay, but even then, I don't really do this. I don't do like kinematics physics anymore. My physics is almost like chemistry physics. So, let's break down the important stuff. So we can get that direction angle. So I should say, I'm gonna repeat this again for like the billionth time, but a vector has a magnitude and a direction. How do you do an ampersand again? Ampersand, how do I write that? I keep forgetting because I don't write ampersands. Looks like that. Magnitude and direction. This direction can be denoted as beta A. I don't like how I wrote that. Which can be found using the Pythagorean theorem and geometry. Found using Pythagorean theorem. I actually am quite bad at geometry. So we'll see how this goes. Geometry! Yay! And the two main equations for this are, we got the classic. The a squared plus b squared equals c squared. But in the vector component form, or I mean, the x and y components of the vector. Sure. The ax, and the ay. And we can also get that direction with the tangent. My head blocking it? No, okay. I know when I like write down here, sometimes my head will block my notes and I'm like writing and no one can see it. And it's kind of sad. Page 35, chapter 2 presents force, work, and friction. It starts with a fable problem. Oh, explaining how ants work, crushing an eggshell, and how archers are strong. Oh, so it like relates things to interesting facts in real life. That's nice. There's nothing about it having electronics. I see. Your courses have fluid mechanics, wave thermodynamics, and modern physics as well. I actually don't know. I don't think mine do. Most of my physics learning actually recently has more been on my own, because I'm not gonna go, I don't want to like dox myself. What I do is very, very specific. So the physics from that, I don't think will ever be taught in a class unless it's a class specifically for that specific thing. If you know what I mean. But yeah. And remember that tangent is opposite over adjacent. I don't know how to spell adjacent. A-J-C-E-N-T? Adjacent. I think that's how you spell it. It's probably wrong. I'm sorry. I'm not very good at spelling. It's something I really struggle with. Luckily for me, there's spell check, so most of the time it's okay. Alright, so we have the AY and the AX. And then we can get that, like, sort of angle if we create this right... I can't see my cursor. We can get this right angle if we get, we create like a right, sorry, we can get the angle if we create a right angle triangle and then calculate the angle using the components of like the opposite and the adjacent, right? Is this correct? Opposite over adjacent? It's been a long time. But maybe we should just use the AX and the AY since it's in terms of vectors. But to continue, when the vector lies either in the first quadrant or in the fourth quadrant, where the component AX is positive, the angle theta in equation 2.16 is identical to the direction angle theta A. For vectors in the fourth quadrant, angle theta is negative, which means that for these vectors, direction angle theta A is measured clockwise from the positive x-axis. Similarly, for vectors in the second quadrant, angle theta is negative. When the vector lies in either the second or third quadrant, where component A is negative, the direction angle is theta A is equal to theta plus 180. Okay. So this is talking about the quadrants. If it's in the first one, you don't have to do anything. You can just find that value. And same thing with the fourth one. Third. Oh no, sorry. No, yeah. Okay. Okay, I see. So you can do the same thing, just like, depending on the quadrant, you might have to add the 180 because of the direction of the angle, I guess, is what they're trying to say. But next we have an example, so let's try the example and see what I know and what all of us know. Second quadrant's negative when the vector lies. The vector in the fourth quadrant negative, which means these vectors. Okay, so when I guess the A is negative, that's when you have to add the 100. I mean the 180. Okay, that makes sense. I understand. I get it. Magnitude and direction of this displacement vector. Oh, we have another example, which means we switch back to green. You move the mouse pointer on the display monitor from that to that, so it's very similar to the previous one, where the magnitude direction of the displacement vector. What are the magnitude and direction of the displacement vector? The displacement vector of the pointer. In example 2.3, we found the displacement. So this is the same example. We identify the scalar components as -4 and 2.9 centimeters. So substitute into equation. So these equations where you can find the A and the angle. So that's your magnitude and displacement component. To find the magnitude and direction respectively. So let's do that. We have example. Hello everyone, are we engineering? I guess so. For now, hopefully. Okay, example 2.4. So we got dx from the previous example. Some engineer fun. Yes, we're having lots of engineer fun. Or engineer suffering, you know, depends how you look at it. There's a fine line. You get that. You got 4 squared, which is 4 squared plus 2.9 squared. Yeah, there we go. Okay, that's really ugly. Just know that's 2.9. and you result in 4.9 centimeters. So this is your magnitude. It should be an A, not a G, and then there's a G. Magnitude. And then we want the direction, so we can do that tangent. We have that component, which would be our AX. So -4 is in the denominator. We have positive 2.9 in the numerator. Find this. I don't have a calculator on me right now, unfortunately, but if you would, plug in basically the inverse tangent like symbol, and then 2.9 over -4, and then you can get your theta, which they found to be negative 35.9. And because of this direction, it lies in its second quadrant, because if you remember how we wrote it out, I thought it should be in the third, no? I forgot which quadrant goes where. 90. Like negative. Let me think about this. I need to think for a second. And I also need to sneeze. Alright, sorry for sneezing. Use your mind calculator. That's very true. I should. If I had a mind. So I think I lost it a long time ago. Ugh, I hate allergies so much. Alright. So why is this in the second quadrant? I always thought it would have been... Oh, I know why. It's because the negative... Oh, okay. So how do we find the quadrant? It's because of the positive or negative x direction. So because we have y is positive and x is negative, that means we're in the second quadrant, which makes sense. And that's how you figured it out. I don't know why it took me so long. It's been a really long time to learn this, but yeah. What's going on with the vectors right now? We're learning how to calculate them. So we get the magnitude and the direction. Bless you. Thank you. Hard thing to learn. Gotta go to sleep. It's 12 a.m. Yes, please sleep. Do not stay up for any of my streams ever. Never do that. It's not worth it. Trust me. I know. Okay, let's get back to the green. And because it's in the second quadrant, I should write this. Because it's in quadrant 2, we can get that angle. So we get negative 35.9 plus 180. And then 144.1. Yeah, okay. And then we can do our checker understanding. Check. I'm just gonna call it check 2.5 instead of writing out the whole title. But yeah, checker understanding. So, we got this previously. We can find the magnitude and direction. I dropped my pen for a second. We have the I hat. Which means our dx is -5. dy is... Oh no, I actually need a calculator for this. Alright. Let me get my calculator. I got my old crusty calculator. Hopefully it works. Forgot how to change it from radians to degrees. How do I change that from radians to degrees? Because I want to write it in degrees. My calculator right now is in radians. I could write it in radians, but I don't think I will. Oh. Okay, I figured it out. I got it. So because we got 2 negatives, if we look at the quadrants, we have it in quadrant 3. So 2 negatives means we have it in quadrant 3. Which means we have to add the 180. So if we want that displacement, we have to add the 180. How do we know that it's an 8? How do we know at which quadrant if the angle lies in? If it's negative, we add 180 to it. Oh, okay, so quadrant 2 and quadrant 3, you have to add the 180. So if you look at where I am in the textbook, the pointer. So you notice how like the A and the Y's are what tell you which quadrant it is. So once we get the like dx or the dy components, you look at that to see whether or not it's negative or positive, and then you sort of match that with which quadrant it is. So if they're both positive, so the dx or dy is both positive, we have it in the 1. If we only have the dx as negative and the dy as positive, it's quadrant 2. And in quadrant 2, you add the 180. For quadrant 4, you don't add the 180, and that is when the x is positive and the y is negative. And quadrant 3, you add the 180 because they are both negative. Basically, I guess when the x is negative, so the x component is negative, then that's when you add the 180. But to tell the quadrants, you base it off of the signs here. But yeah, I wish they kind of explained it. I got a little bit confused of it too, and then I remembered. Or I figured it out. But yeah, after this, like, check my understanding 2.5. I'll write a note at the bottom just so that it's really set in stone within the notes. Let me get my pen. Okay. So we can take our magnitude value. By that, we take this. It would be 5 squared. It's like 25 plus 9 in this case. And then square root that. 2, that should be a 2. I honestly, I don't remember how to use this calculator much. Squared plus 9 squared. So, it could be wrong, just so you know, please. Check my calculations, because I have not used my calculator, my scientific calculator, in a long time. Usually, I just pull it up on my computer, where I, like, do something like that. So we'll just keep it like that. So that's our magnitude. Magnitude, and then we can get our tangent. So we have 9, not 9, 3. 3, not 9. 3 over 5. And we can find this by doing that inverse tangent symbol thing. If I can find it on my calculator. Okay, I got it. 3 over 5. 30 degrees, 30.9. 0.96. Yeah, 30.96. And that would be our theta. But then we need to find the angle displacement, which means we will add this to 180. That's a 6, not an 8, plus 180. Then we get 21.096 degrees. So 210.96 degrees. And I think oh, it doesn't say. I was gonna be like, well, the previous one gave us the example. Wow, we have a lot more to go. Am I gonna finish this section this time? Maybe not. Oh, wait, I skipped it. Did I skip a section? 2.2. I want to finish 2.2. I feel like, oh, okay, it's right here. So it's feasible. I think I can finish. We can finish. As long as my voice does not go out. I think I might be getting sick, to be honest. Because I've had a sore throat yesterday. Don't know why. I hope it goes away. And I hope it's not me being fully sick, but... Okay, I'll stop rambling. Sorry. In many applications, the magnitudes and directions of vector quantities are known, and we will find the resultant of many vectors. For example, imagine 400 cars moving on the Golden Gate Bridge in San Francisco in a strong wind. Each car gives the bridge a different push in various directions, and we would like to know how big the resultant push can possibly be. We have already gained some experience with the geometric construction of vector sums, so we know that the task of finding the resultant by drawing the vectors and measuring their lengths and angles may become intractable pretty quickly, leading to huge errors. Okay, worries like this do not appear when we use analytical methods. What do they mean? Okay, so they said that, instead of just purely using, the drawing things and, drawing stuff, which can lead to a bunch of errors, maybe finding, an analytical method as purely based off of numbers is the way to go. The very first step in an analytical approach is to find vector components when the direction and magnitude of a vector are known. Let us return to the right triangle in figure 2.18, so that would be this one. The quotient of the adjacent side ax to the hypotenuse a is the cosine function of angle, so theta a is equal to ax over a, so that's your cosine theta a, and the quotient of the opposite side ay to the hypotenuse is the sine function. So yes, so more geometry, more angles, where ay over a is equal to sine a. When the magnitude a and the direction theta a are known, we can solve these relations for the scalar components. When calculating vector components in equation 1, 7. Care must be taken with the angle. The direction angle A of a vector is the angle measured counterclockwise from the positive direction on the a-axis to the vector. The clockwise measurement gives a negative angle. Okay, so the direction angle A of a vector is the angle measured counterclockwise from the positive direction on the a-axis. So clockwise gives a negative angle. I'm not fully sure what they mean, but let's continue. Maybe they'll explain it in the example. But I think what they're saying is that we can find the angles using other methods of geometry, and we might not need both A and Y components. We might just need the resultant and the A. But regardless, let's write cosine A. You can find it with the AX component over A, and the sine, you can find that theta A with the AY and the A. This section has a lot of examples. Okay. Example 2.5. A rescue party for a missing child follows a search dog named Trooper. Trooper wanders a lot and makes many trail sniffs along many different paths. Trooper eventually finds the child, and the story has a happy ending. Okay, but his displacement on various legs seemed to be truly convoluted. On one of the legs he walks 200 meters. I wanted to say miles, but I'm like, miles is not at all correct. 200 meters southwest. Then he runs north some 300 meters. On the third leg, he examines the scent carefully for 50 meters in the direction 30 degrees west of north. On the fourth leg, Trooper goes directly south for 80 meters, picks up a fresh scent, and turns 23 degrees west of south for 150. I'm losing I can't read. Find the scalar component of Trooper's displacement vectors and his displacement vectors in vector component form for each leg. It seems overwhelming at first and gets easier. Yes, it definitely does. Alright, so he's got like 4 legs, and that's great. On one of the legs, he must run some north. On the third leg, he examines the scent. On the fourth. So he's 3 legs of search. 1. Okay, on the third leg. So there's no second leg. I guess we have to find out what the second leg is. Okay, well, strategy. Let's adopt a rectangular coordinate system with the positive x-axis in the direction of the geographic east, with a positive y direction pointed to the geographic north. So they drew a coordinate plane. So this is our north. AKA also our Y as well. No, it should be this way. This is our east. And our X as well. And let me erase this side. I don't know why I thought it was the other way around. Oops. Okay. explicitly the unit vectors I of the x-axis points east, and the vector j hat of the y-axis points north. Tuber makes 5 legs, so there's 5 displacement vectors. 5? I thought there were 4. Okay. There are 5 displacement vectors. We start by identifying their magnitudes and direction angles. We use the equation 2.17, that would be these, to find the scalar components of the displacement in equation 2.12. Maybe I'm gonna write both of the equations. I'm just gonna write the equations here because I don't want to keep scrolling up, and I'm very forgetful. We have that, and we also have these two as well. Okay, on the first leg, the displacement is L1 is equal to 200. That is given with us right here. And the direction is southeast. For direction angle 0 to 1, we can take either 45 degrees measured clockwise from the east direction, or 45 plus 270 measured from the counterclockwise from the east direction. With the first choice, how did they get that angle? Oh, wait, I see. So he runs like up. Wait, no. Get 45 from the east direction. How do you get 45? The second choice, we get positive. You can use either of these two angles. The components are that. Okay. "45 degrees. Walks southeast and runs north." So he goes southeast, which is like this way, then runs north. And that would be... Oh, I see. Okay, southeast. Yeah. Sorry, I get it. Yeah, southeast. Draw southeast. You're absolutely correct. Hello. Hello, greetings. 45. I see. I'm really bad with directions. But thank you. Thank you for the clarification. So, I guess they wrote it as L. So we got L1, which is 200. And I'm going to do the positive one that they did as well. And then because... going north. Oh. So to find that y component, we use a sine of it. That makes sense. 200 sine 315 114 meters. And then I guess that is our full vector of the first leg. Okay, my voice is starting to slowly give out. So I don't... For these check your understandings, I think I'm gonna like skip them. Because we're almost done. I'm sorry, I wish I had like more stamina. You could use 45 to get the same result. Wouldn't I have to? It would be negative 45, but yes. Higher. Sorry, but yawning. Higher angles makes it harder. Really? I always think positive angles are much easier to work with than negative angles. I guess it depends on the person in that regard. And we can get our final... I'm gonna get water. Oh. After this, let me get some water. We got in meters. Second leg, wandering to the magnitude and displacement, and the direction is north. Oh, I see. Okay, so this is the second leg. Okay, I just can't read. I feel like that was an English problem. And before you ask me how many languages I can speak one, and it's the one I'm speaking right now. Okay, let me get some water first. Okay, shall we continue? So, for the second leg, it's 300 meters and north. We go north. $300 Because it's north, it's 90 degrees up, so you use a positive 90 degrees. So that means you can get this. Positive 90. Have you studied chem and bio too? Not bio. I studied chem, but I'm not very good at it. Yeah. I studied a little bit of bio, not too much. For me, I actually didn't really need to take too many bio classes. I just needed to take one, and it was more like general education versus anything more difficult. It's not... For chemistry, I did have to take like engineering chemistry, but only like the first two classes, so I never needed to take like OChem. I never needed to take organic chemistry. For physics, I had to take 3 of them? 4? No, 4. I took 4. And cosine of 0, or cosine of 90 is 0. You were more inclined towards coding, I assume. Actually, not really. I don't really know what I do anymore. I don't know what I do, honestly. I don't know what I do every day to myself. I used to say I used to do more coding, but not anymore. I actually don't enjoy coding. I guess you could say that what I do now is more physics-y, but it's not like this type of physics. Yeah, VTuber all the way, exactly. I'm a stupid VTuber. I'm just a stupid VTuber. And all I do is I rot all day. I have brain rot in my head every day, all day. I've recently learned of, what's it called? Italian brain rot memes. And like, they're so stupid that they're great. Rot maxing, yeah, exactly. I'm pretty sure I wrote the notation incorrect. Yes, I did. I wrote it correct there. Yes, no. Because we got 0. I actually don't know that one. I know the ballerina cappuccino. I know the trallaleo tralala tralala. Oh my gosh, what's wrong with me? And I know that there's like a tree one or something. But yeah. I have not heard of Pomerino crocodile. I haven't heard of that one yet. So maybe I'm not 100% brain rot maxing just yet. Okay, 50 meters. The direction of 30 west of north. 30 west of north? Okay, so 30 west of north. 30 west would be like here, sort of. Oh yeah, tung 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 sao or something. Oh my gosh, what's wrong with me? And respectfully, okay, I don't mean this in a mean way, but respectfully, what's wrong with you too? Respectfully, why do both of us know this? This is not good. I still never seen Skibbity Toilet or whatever it's called. I never seen that. So I guess there's some I still have some faith in me. I'm not with the youth. I'm very old, tired. I'm about 8,000 years old. I'm also from a different dimension. Speaking of which, I definitely still need to post my lore video and my, like, debut highlights, which I am still editing, and it's gonna take me probably like another month, and I'm so sorry about that. I suck at video editing. It's something that I need to get better at with, or get better with. 50 meters, got cosine, 20. 3y, we do the same thing, but we have sine. 120. Was that 40? 43.3. Yes, Kiwi Toy is totally not in league. There are leagues of memes now. There's different leagues of memes. That's funny. Yeah. So yeah, what was it? -25. Right? Yeah. Got the I hat plus 43.3. Please introduce your VTuber avatar. I don't know any lore. Oh, my lore is that I am a failed engineer. And I am like in this body because I wanted to create a robot friend and I couldn't figure it out, so I went to a wizard because we have magicians in my dimension. And in my dimension, I turned into this mess, but the wizard felt kind of bad, so he helped me and allowed me to see the internet dimension, which is this dimension that I'm in right now. And yeah, that's that. If you go to my like debut, it's sort of recent, my debut stream. That's like the first thing that you should see besides like the loading screen. Fourth leg. South. That's 180. Right? Or -90. Oh, 270. Sorry, not 180. 80 is west. 180 is west. South is 270. That's correct. Okay, I get it. I have a brain. It has not all rotted away yet. Surprisingly. Oops. But yeah, when I'm not talking about like this stuff, I like to play a lot of games. I guess to anyone who's new, I see a lot of new names in the chat, but today. For today. I am Blueberry. You call me Blue or Berry or whatever. And I like to play mostly like cute and cozy games, but I like to include education in as well. So my goal in streaming overall is to help inspire someone to try something new. But yeah, I usually play like farming games or like very, very cute puzzle games. I recently also started getting into a few visual novels. I like Baldur's Gate a lot. I guess that's not a cute game necessarily. I don't know why I'm copying the thing. But I like Baldur's Gate a lot. I like adventure games as well. Adventure games are the best. But any combination of that is good. Stardew Valley, yes. Metroidvania. I've never heard of that. Is that a genre? Or maybe I have and I don't really know. Zero. We got the y component because the x component cancels out with the cosine 7. 270. What are we learning? We are learning about vectors and how to calculate the vector components for directions, and as well as the magnitude. But yeah, so we're learning about vectors on a coordinate system. And specifically, in this case, we have the x and y coordinate system, so like a 2D coordinate system. What else? Yeah. What else did we learn today? That's it. At the end, I'll definitely do like an overview of everything. But the book is free. I have it pinned in my chat. I should have it pinned in my chat. If not, it definitely is in the description, hopefully. But if you like to follow along, feel free to. Or if you just like to sit and chill, feel free to as well. Okay, so we got the magnitude of the fresh scent and turns at. So we got 150, so that's the magnitude. It turns 23 degrees west of south. 20 degrees, oops. 20 degrees west, so west of south. So slightly like this way. So we got the 270 plus the 20, I think. West of south. Subtracted by 2? Oh yes, because it's going the other way. I'm really bad. Okay, I'm gonna write out the coordinate system again, because it's all the way up there. Let me move this. What are the real life applications? Everything, if you think about it. But mostly this is like university engineering focused, so there's a lot of like theory behind it. But basically with the vector systems is that it can tell you two pieces of information. For example, if you want to figure out which how something displaces. So if something goes from one spot to another, you can find not only the distance but the angle, and aka the angle is like the direction of where it moves. In this case, I guess this is sort of real life applications. They're making us calculate the displacement of a search dog. So they're saying that the dog went here, here, and here. So can we find that angle and that distance that this dog went? Although I know it seems kind of like hard for people to see where what goes to where. Like, are you actually gonna like calculate a displacement of a dog with this? No, probably not. But it's important to learn the skills to apply that to later on things. So yeah, I know that like calculating the displacement of a dog is not very that important, but let's say if you want a train, or you want to figure out which where specifically to build a train and what are the limitations of the train. Let's say the train can only turn like the limitations are, well, it can't really turn too fast, but we still want to place it. We want it to go from one place to another. So like, which angles should we sort of place the train tracks, or should we build a train to like make sure that everyone is safe and stuff. But yeah, for the average person, and that includes me, am I going to use this on my day-to-day? Probably not. It depends what you do. Like, do people use stuff like this in real life? Yes. Yes, for rockets and stuff too. Exactly, yes, for rockets. A lot of space stuff. But your average person, day-to-day, doesn't really use it, and that is actually, I would say, quite accurate. So we have like 270 down here, and then we have, was it 23? 23 south, west of south. So, and then we subtract that 23. Yeah, okay, I need to get better at these directions. I have no sense of direction. But I think if I draw it out, I can figure it out eventually. Wow, this example is so long. And I kinda... am funny. And we get cosine 247. Oh no, not cosine, that should be sine. Two, 247. Oh, and there should be negative here. 138.1 meters. Let me get the final vector component with negative 58.6. And what is that? Minus 138. J. Then we can have the meters. So that is a lot of vectors that this dog went through, but they are 5 sections. There are 5 places that this dog went to. This dog traveled a lot to find that kid. But good. Good on the dog. And bad on me for not knowing my directions. Rockets, ain't that about controlling trajectory other than calculating displacement? Well, I mean, there's various things to find where a rocket goes. I don't really know the details, because obviously I'm a failed engineer for a reason. It's in the title. But yeah, I'm sure you might be able to like locate where something went, or honestly, it's how are you gonna figure out trajectory if you can't calculate vectors? You gotta build up your skills too. But if you don't want to learn vectors, feel free to. Like, you don't need to learn it if you don't want to. This is just for fun. Nothing too impressive or spectacular is going on here. We're just learning for fun. I mean, there must be a reason, right? They teach it in schools. Alright. Coordinate, or polar coordinates. Let's continue on. Let's get back to my blue note-taking, thing. And wow, most of it today was mostly examples. There weren't that many actual notes. Interesting. Okay, polar coordinate. Polar polar coordinates. To describe the locations of points or vectors in a plane, we need two orthogonal directions in the Cartesian coordinate system. These directions are given by unit vectors I and j along the x-axis and the y-axis, respectively. The Cartesian coordinate system is very convenient to use in describing displacements and velocities of objects and the forces acting on them. However, it becomes cumbersome when we need to describe the rotation of objects. When describing rotation, we usually work in polar coordinate systems, okay? In the polar coordinate system, the location of point P in a plane is given by two polar coordinates. The first polar coordinate is in the radial coordinate r, which is the distance of point P from the origin. The second polar coordinate is the angle phi. I think that's phi. Then that the radial vector makes with some chosen direction, usually the positive x direction. In polar coordinates, angles are measured in radians or rads. Why not in degrees? Well, it's polar, that's why. The radial vector is attached at the origin and points away from the origin to point P. This radial direction is described by a unit radial vector r. The second unit vector t is a vector orthogonal to the radial direction r. The positive t hat direction indicates how the angle phi changes in the counterclockwise direction. In this way, at point P, it has coordinates x and y in the rectangular system, which can be described equivalently in the polar coordinate systems as r and phi. This equation is valid for any vectors, so we can express the x and y coordinates of vector r in this way. We can obtain the connection between the polar coordinates and the rectangular coordinates of point P. Alright, so polar coordinates. Alright, talking about rockets now, huh? I see. Let's try to keep it on topic, but I guess it's up to you if you think this is useful or not. Coordinate systems are directions given by vectors I and j along the x-y axes, describing displacements, however cumbersome when we need to describe the rotation. So, coordinates are great for describing the rotation. Polar coordinates for rotation. It is one of the applications, but also I'm trying to teach it, and it's a bit hard for me to sort of teach it and try to explain something about rockets. Just I don't to be honest, like I said, I'm not an expert. I'm doing this for fun. So I'm gonna continue talking about polar coordinates, and if there are rockets brought up again, then in the text, then sure, but I want to continue focusing more on like the teaching aspect of it. And please respect that. Rotation. Okay, so we need rotation, and then we have two polar coordinates. The first one two polar coordinates. We have the radial coordinate r, so this is our radial coordinate. And then we also have the second part. So we have the angle phi. And it makes some chosen direction, usually in the positive x direction. And polar coordinates angles are measured in radians, so angle phi and make sure that it is in radians. The radial vector is attached at the origin and points away from the origin point to P. So, radial vector, I guess we can draw it a little bit. Yes, I think I'm gonna redraw this so that we can show how it looks. Got radians. Got the R this way. And we have that angle. Yeah. 1 rad equals 2 pi. I don't know. I don't remember. I definitely know that you can change the... You can sort of convert degrees to radians with 2 pi, but does it equal 2 pi? Maybe? Yes? Or is it's either 2 pi or 1 over pi, and I don't remember. Let me search it up really quickly. Oh, no. It's 180 over pi. Okay, so 1 radian equals 180 degrees over pi. Yeah. So you have to use the degrees to sort of I guess switch it. You gotta use that degree conversion. It's not just like 2 pi. Right, because in that unit, there's like I remember, I don't know if anyone has like learned this before, but there's like this circle of units, and it's like, ooh. And okay, just pretend that those are straight, and this is like 0, this is 90, this is 180. And then we got like 0, and then pi over 2, and then we got like pi, right? And then you can use that to convert it. Yeah. Yeah. And then we got like 3 over 2 pi, you know, and then we just got 2 pi here. This is one circle. And that's also like 360. 2 pi equals 360. Yes, exactly. Like that. That's how you convert it. I remember this. Okay, let me erase this because it's not really needed right now. Oops. And then we have, in this way, we obtain the connection. So let's write the connection between the coordinate system, the Cartesian coordinate system. So that with the x and y, and the polar coordinate system. So got the, I'm gonna call it cart system, just as a quick thing to polar. So I don't want to write it all out. Save some space. Thank you. No problem. That I do remember. I remember that you like that like circle so much because I struggled so much trying to learn it. Like when I first saw it, I remember we were supposed to memorize it, and I just could never memorize it no matter what I did. But even now, I still don't know all of it. There's supposed to be like more in between the circles, between like the 90s and the 180s and the 270s, but I don't remember. By the way, this is how I'm gonna write my phi's. I know that this is like a capital phi, and the way that it's denoted in the textbook is a lowercase phi. But I don't know how to write this too well. Every time I try to write that, it looks ugly, and I don't like that. Like, it doesn't look like how it's supposed to look, you know? So I write it like this. I just hope that the notation won't get confused, like there won't be a capital one. Just know that this is phi, and when I say like this, I relate it. I mean like the lowercase one. It's just how I write it. And then we can get our endpoint, which our endpoint is point r, and that one. And then we got the examples. There we go. We have another example. We got a lot of examples today. So, a treasure hunter finds one silver coin at location 20 meters away from a dry well in the direction 20 degrees north of east. So that's one bit of information. We have 20 meters from the dry wall, direction 20 degrees north of east. North of east. So that would be 20 degrees north of east. I still don't understand how they say things. I know it's somewhere here. It's either 20 degrees from the north or 20 degrees from the east. 20 degrees north of east. So it should be 20 degrees north of east. So like this, and this is 20? I think. And then we have one finds one gold coin, so gold coin location at 10 meters from the well in the direction of 20 degrees north of west. North of west. So we have this one. Nope, stop. I don't like when the thing does that. So we got north of west. 20 degrees north from the west. So I'm thinking this. It's either that or this should be 20. I don't know. The way it's described to me seems like this. What are the polar and rectangular coordinates of finding these in respect to the well? Okay, so we got a dry well, and that will be our origin. So the origin will be the well. The well marks the origin of the coordinate system and east in the x plus direction. We identify radial distances from the locations to the origin, which are RS is 20 for the silver coin and RG is 10. Okay, so they take this and just turn it into a radial direction? A radial distance? So we got, I guess they denote it as RS for silver and RG. Imagine a storybook using the form of sentences to explain story. That would be pretty annoying. I don't read. I don't read anymore. As I've discussed earlier in the stream, I've been brain rotting all day. I've been girl rotting, girl crying, and brain rotting all day. Okay. So, to find the angular coordinates, we convert 20 degrees to radians. Oh, here's your conversion. If you're still there, Pickle. Hello, Pickle, by the way. If you're still there, you can see the conversion here. So we got it in degrees. So this is your degrees. And this is equal to pi. 20 over 20 over 180. So we have the degrees, we can cross out like this degrees stuff, and then we can get it in radians, which is 9. I think radians. So that's how you would calculate it. You can use equations, 2.18 and 2.18 to find the x and y coordinates of the coins. So we can use this equation, which is xr cosine, that, and this. R sine that. Yeah. There we go. Is my head blocking? My head is blocking my big, ginormous, annoying head. Sorry if I was blocking too many things. So yeah, sorry. I guess you weren't able to see this, but I wrote the radial coordinates as this. But yeah. Okay. Man, I'm also a failed engineer. Oh, welcome to the club. I'm still trying to not be a failed engineer, but we'll see. I'm still trying not to be a failed engineer. The angular coordinate system of the coins has, so for the silver one at least, we got that 20 degrees for 20 degrees this direction, whereas the angular coordinates of the gold coin is that. Oh, minus. Okay, I wish they had explained this, but for the gold coin, so I guess I am correct. It is this. So for the silver one, which is the first one up here, so this is silver, and then we got the gold. I'm yet to be a failed engineer. That's good, that's good. Unless you want to be a failed engineer, and you call yourself a failed engineer. I failed, but I'm trying. I'm trying to unfail. Okay, so we have this, and then because, like, as I said, in that like little circle thing, we have like the 0 and pi. We can just calculate that difference. Oh, I should use capital G just like the other one. We can calculate the angle of the gold coin just by using that like pi here, because it's all in radians. So 9. So we have it as 20 this way. So that it means plus 20. But then because we need it to be 20 this way, we can take the 180, so the pi, and subtract that 20. And then we are able to get this angle right here. In which case we get 8 pi over 9. Oops. Why is my penmanship so horrible? 8 pi over 9. But yeah. Okay. So with that, we can get our S and the phi S as the radial component, which is the distance in this case, or the magnitude, and then we can also get the angle. There we go. In radians. Make sure it's in radians. We get G. Just 10. Ooh. So we get 10 and 8 pi over 9. Right? Yes. Okay, we substitute these into the equation to obtain the regular coordinates for the gold coin. Okay, so we can each get the x and y component from this. So we take each one and do that. So let's start with the silver. So we got our radial component, which is 20. And then we got cosine, pi over 9. I don't have a calculator, so I'm just gonna trust the book. What did you study? I am still studying, well, okay, when I say this, please do not ask for me to solve questions, because I'm very stupid, okay? There's a reason I call myself failed, but I study ECE, so electrical and computer engineering, and I'm still studying ECE, technically, although sometimes yeah. Don't ask me to code, because I don't know how to. Please don't ask me to solve things, because I don't know how to. I'm very bad at everything I do. And then we can do the same with the gold. We get 10. Oops. Cosine. 8 pi over 9. Which where's that? Okay, they got it at negative 9.84. Or 9.48. Where does the 8 come from? 9.4, negative 9.4. Y, G. This, we got sine 8 pi over 9 and 3.4 meters. So that is our x and y. So for silver, our x and y is equal to 18 point. That's an 8. 18.98. 18.9 and then 6.8. And they're all meters. For the gold, we have xy negative 9.4 and 3.4. And also in meters. Yes, okay. Are you ready for, I think, the last section? And it's good. This is the last section, because I think my voice is gonna go out. I love streaming these sort of things, but every time I do, it's really straining out my voice, because I feel like I have to talk all the time, versus when I play a game. I feel like the game can talk for me. I'm gonna take another sip of water and hydrate myself. Please do the same if you feel like it. Okay. Chug, chug, chug. Yes. That's amazing. Good luck. You can do it. Thank you. We'll see. We'll see in a few years. But I will still keep... Here's the thing. Even if I pass, you know, even if I continue and I actually get what I want to get from this, will I still... I will still feel like a failure, you know? I'm that type of person. So we are in the next part of the section. So vectors in 3D, 3 dimensions. Okay. To specify the location of a point in space, we need 3 coordinates. So x, y, and z, where coordinates x and y specify locations in a plane. The coordinate z gives a vertical position above or below the plane. 3-dimensional space has 3 orthogonal directions, so we need not 2 but 3 unit vectors to define a 3-dimensional coordinate system. In the Cartesian coordinate system, the first 2 unit vectors are the unit vector of the x-axis I and the unit vector of the y-axis j. The third unit vector k is the direction of the z-axis. Okay, so instead of just having that I hat, the j hat, there is now a third component, like a vector, another unit vector, sorry, not component, another unit vector that is k hat. The order in which the axes are labeled, which is the order, wait, what is this sentence? The order in which the axes are labeled, which is the order in which the 3 unit vectors appear, is important because it defines the orientation of the coordinate system. The order xyz, which is equivalent to the order ijk, defines the standard right-handed coordinate system, so it's got a positive orientation. So in the 3-dimensional space, vector A has 3 vector components. The x component, so we got that a xi, which is part of vector A, along the x-axis, the y component, which is the ayj hat, which is part of the x-axis, and the z component, which is the az and then k hat, which is part of the vector along the z-axis. A vector in three-dimensional space is a vector sum of its three vector components. So that's a lot. Will I practice later? What do you mean by practice later? The chat box can't contain my knowledge. That's true. But also, knowledge sometimes should be shared outside, depending on what things are. Alright, 3 coordinates. So in this case, let's like define the specific coordinate system. So 3 coordinates. So we got the x, y, and z. Coord, x, y, and z. Ah! Sorry, I clicked on a button on my pen. Hopefully that didn't screw anything up. Coordinate systems. Third-dimensional space has 3 orthogonal directions, but we need not 2 but 3 unit vectors. Okay, so x, y, z, and then there are also 3 unit vectors. I, J, and K. What the heck? Make sure don't forget the hats. And make sure that they are ordered correctly. So let's type in order of the unit vectors matters. Order of unit vector matters. Because they have corresponding. Of unit vector matters because of corresponding directions. So we'll put because of corresponding directions. So how do I corresponding? I probably spelled that wrong. Directions. What are you guys talking about? What? Incorporate? How do they incorporate 4 and 5th dimension, time, space, and coordinates? I don't know. I have no idea. This is beyond what I know. Okay, and then the 3-dimensional space. We got the x and y. Alright, at the end, maybe at the end of this section, I can search up the whole thing about rockets, and if it's possible, if there can be a 4th and 5th dimension thing. But for now, let's try to keep it on topic. I will search it up at the end, but it won't be like anything in depth. Like I said, I don't know too much, and I'm just an idiot. I'm trying my best, okay? This is my best. I know it's not good. But we can search up those questions like quickly after. Okay, and then our vector sum can be shown as in this form. if we know the coordinates of its origin, so we have the beginning. Oh, it's the same thing, just like but just like 3 of them instead. So we got the beginning and end. Its scalar components are obtained by their differences. So we have the ax component and the ay component are given by that equation, and then we have the same one. So basically it's the same. And we can also get the magnitude, I guess, by like doing the same thing like in 3 dimensions. This expression for the vector magnitude comes from applying the Pythagorean theorem twice, as seen in this one, so 2.2 figure. Magnitude A is obtained by generalizing that. Okay, the diagonal in the xy plane has a length of the regular Pythagorean theorem, so that ax squared plus ay squared, and its square adds to the square az to give our final magnitude over a. Note that the z component is 0 and the vector lies entirely in the xy plane, and its description is what? Oh, reduced to 2 dimensions. I was like, is what? I don't see anything. I just see a figure and there's just an example. It's reduced to 2 dimensions. That's the weird thing. I don't like that. They should have just put this entire paragraph on the next page, if it's gonna be just like 4 words on the one page. But anyways, so you can do the same thing as in 2 dimensions with the whole begin and end. Same as 2D with b, xb, and yb, and zb with, there should be an h, with and now I'm gonna put an ampersand again, like that, with e, y, e, and z, e. So you can subtract the end and the beginning to find component values. Can subtract end with beginning, or I'm just gonna write begin to find values. Find values. Yeah. And then we can also find the magnitude. It says z component 0, so it goes back to being 2 dimension. What? Oh, I see. I see what you're talking about. The last thing. Note that when the z component is 0, the vector lies entirely in the xy plane and description is 2 dimension. Yes, I see. But I was so confused. I just don't like how this is not connected to this, and it's making me annoyed. It's just when I look at it, you know, it's just like, ugh, why'd you do that? But yes, when z is 0, it goes back to 2 dimension. Let's add that as well. So we can find the magnitude, but I'm gonna go in. So we can find the magnitude. Magnitude A with this. So you just add the Pythagorean theorem twice, basically. And since they're equivalent, you can just do this. Oh, that's 2. And that's a 2 too. Z2. If Z component equals 0, it's 2D in XY plane. And becomes a Cartesian coordinate system instead. Amy calculating cube here. What's up with the 2 dimensions? Do you mean like cubed? So basically, to find the distance, it's still like geometry. You're doing two of the Pythagorean theorem twice, if that makes sense. So you get like the xy plane, and then you add on that z component with that a squared. So you take that and then do the Pythagorean theorem, and then add this on to that z to the az. I'm sorry. You take that the xy plane distance, and then you add on that z component, which is another Pythagorean theorem operation, and that would give you a. But because it's like the same thing, you could just include it into your first equation to begin with. And then if the z component is 0, which means all of this is 0, so there's no z component at all, you end up just getting what we got for the Cartesian plane, which is just the x and y. But yeah, basically we got 3 axes, so it's like a cube, and we can have this this vector here that has the x and y and z, but pretend that we don't have the z. So we would just have like it flat. I can't really, well, actually I'll try drawing it out, and then we'll see what happens. Is this classical mechanics? Not yet. I think we will get into it eventually, but it's gonna be a while before we actually get to the mechanics part. Or any like motion, any like true motion. Like by motion I mean like acceleration and things like that. Right now we're talking about like vector displacements. So we got that. X, Y. X, Y. And Z. This is high school level geometry. It is. It's the very first chapter of university physics. If you, like I said, if you want to actually learn about university physics, go to the book. You can go at a much faster pace. I'm just doing this for fun because I want to, and I think that like maybe people who don't have the same background that I do might be just interested in learning something new, and that's mainly why I do it. I just want to see if anyone is like interested in learning something new. Let's draw the box. Okay, this is really bad. Oh boy. Okay, this is really bad. And then sort of like that. And then I'll draw like a vector in red, just like the example. Kind of like going up here. Ugh. It's so ugly. Maybe I should complete the box. Yeah, let's complete the box first. Should do that. Okay, here's the really crappy box. But there it is. Let me erase this. It shouldn't be there. Okay. And we got like this vector comes here. Got the A. Has the A X plus Y. Let me redo that. I'm gonna like write it like this. And I'm gonna write it smaller. Yeah, okay, there we go. But basically, when the z vector goes away, instead of getting this again, you get just a flat plane. So you get like that. Which then becomes your Cartesian plane, which is just the x and y. But yeah, I guess if z is equal to 0. Do you think that vector goes away or the opposite? What do you mean? If it were to go the opposite direction, it would be negative? I'm kind of confused on what you're talking about. Why remove the z? Oh, it's just an example. There's nothing why. It just means that, like, if the z component is 0, then it becomes a 2D plane. This is just to, like, show it. Nothing really much. S Y system. Okay. And now, shall we finish off with our last example, and then talk about stuff quickly after. Oh my gosh, it's ready. I did not expect to be live for this long, I'm gonna be honest. I thought it would have been done. That's okay. Who needs to do responsibilities when you can just become VTuber all day? No, I want my pen. Give me back my pen. Example 2.7. Okay, during takeoff, the AIA Heron, its position with respect to a control tower is 100 meters above the ground, 300 meters to the west, or to the east. Sorry, I can't read. And 200 meters to the north. 1 minute later, its position is 250 above the ground, 200 meters to the east, and that many 2,100 meters to the north. What is the drone's displacement vector with respect to the control tower? What is the magnitude of its displacement? So we have like two, so basically it goes from one spot to another. So we got 200 meters straight up. So that would be our z, right? That's your z, I think. We've got 300 east. So that would be degree 0, or I guess 2 pi or just 0. And 200 meters north, which would be 90 degrees, or pi over 2. Yeah, okay. Strategy. Take the origin of the Cartesian coordinate system as the control tower. The direction of the x-axis is given by the unit vector I to the east. The direction of the y-axis is given by the unit vector j to the north. The direction of the z-axis is given by the unit vector k hat, which points up from the ground. Okay, so east, we got this. We got the I. And we got the j. And then we have the k component. The drone's first position is the origin, or the beginning, of the displacement vector, and its second position is the displacement at the end. Okay, let's write the second displacement. So this is the origin. This is our start. Later, we have it at 200 meters. That will be our k component. 120 meters? Or not 120, sorry, 1200. 1200 east. So that would be our x component. And then we have that. Meters, and that's our north component, which is, in this case, the j. The drone's position is the origin, displacement is the second. Okay, so we are gonna do the same thing where we can take that magnitude. So we take the end and subtract it with the original. So for, I guess they're going dx, dy, and then dz. So let's do that as well. dx, for dx we have this, minus 300, because we end at 1200, but we start at 300, and then we get 900 meters. We have the dy, which is the j component, same thing. Is this the last section of today? Yes, it is. I didn't realize how long I've been live, actually. I only predicted to be live for around 2 hours. I do have to do things after, but I promise that I still will go over whether or not, will just quickly search it up, whether or not it's possible to have a 4th and 5th dimension, and what vectors and rockets have in common, or what can you use it for. But yeah. We'll have this. And then we'll have dz, which would be 250 minus 100. So we get 150. That's 100. 150 meters. That's our displacement. And then we can take that into that form. So we get d is equal to 90 90i plus 190 j plus 150 meters, and that would be k. And that is our final. Oh, wait. Units! Don't forget the units. We get that. And then we also should find the magnitude of this, right? So to find the magnitude, that's the vector symbol, by the way. I forgot it. We should do 900 squared plus 1900 squared plus 1500 squared. And I think we should get this, right? Yeah. Oh, yeah. Okay, this is, I have it in meters. Mine's in meters. Theirs is in kilometers. But yeah, I guess that is the last example for today. In terms of this. Okay, let me see your questions. Last section for today. Yes, it is. To the next time, which is in like a month. Like I said, I go very, very slowly. I like to go very, very slowly when I do stuff like this, but I always do this once a month. Next section will be algebra of vectors. Why use the Pythagorean theorem to find magnitude? Because it's an easy way for people to visualize it. Also, it's quite easy to do it, right? It's based off of triangles. You just get the hypotenuse of it, and then you can get the distance. Also, that's what the book says, so... But yeah, let's quickly go over an overall review of the main points, then we'll look at your questions. But so we have coordinate systems and components of a vector. Of course, a vector has two components. We got the magnitude and direction. For the xy coordinate system, there are like two components. We got the x and y components. From that, we can get these, like, they're sort of their own individual vectors, and once you get both sides of that vector, it sums up to another vector. And they are, the x and y in this case, are very much orthogonal to each other, which means they are perpendicular. We did an example about the movement of, I think like a fly or something, and then we got this. So to find that distance, we have the end point subtracted by the beginning point. But yeah, and we keep going. You can use geometry, which is where the Pythagorean theorem comes in, to find that magnitude. So we got the a squared plus b squared equals c squared, but in this case it's a squared equals, I'm sorry, ax squared plus ay squared equals a squared, which is that magnitude of our vector. And you can do this by creating basically a bunch of right triangles and finding that hypotenuse. And you can also find that angle, the direction or that angle of that vector from an origin point or something based off of tangents and cosines and sines. You can also find our vector, our a vector component, or our a vector magnitude, if you just have the ax vector component or the ay vector component, once again based off geometry and using the cosine and sine operations. And then we also introduced ourselves with polar coordinates. So you want to use polar coordinates when you describe rotation. There are two polar coordinates. There's the radial coordinate, denoted as r. We have the angle, which is denoted as phi. And you can convert the Cartesian system to the polar system as well, using a cosine phi and a sine phi with the r in front of them. You get the x and y. And we have the vectors in 3D. So that means there are like 3 axes. So we have the x, y, and z. So that means we have the I hat, j hat, and in this case, the k hat. With this 3-unit vectors system, make sure that the orders of these unit vectors are in the correct order because it corresponds to the direction of your coordinate system. For example, I, j, and k correspond to the right-hand rule, to the right-hand coordinate system. And then we also have like the same thing, so it's basically the same thing, where you have that az component, we got that k unit vector, and then we can get the az vector. You can have a vector sum, same thing, where you get the end point minus the beginning point to find that value. You can get the magnitude again, once again using that Pythagorean theorem, but this time we add a z component to it. We add a z component to it, but yeah. And if the z component is equal to 0, that is a 2-coordinate system. Yeah. Right. What does she mean by failed engineer? It means I'm a failure of an engineer. That's what that means. Okay. Is it possible? Isn't magnitude connected to frequency instead? So magnitude is a value. Frequency is how fast something's oscillating. I guess I see that you're talking about earthquakes. So earthquake magnitude, I actually do know a little bit about this. But like I said, take everything with a grain of salt, okay? I'm an idiot. I'm a stupid idiot. I don't know. So when you have like a measurer and there's an earthquake, it like does like this, right? So your magnitude is how high this goes. Your frequency is how fast these like peaks are, but yeah. Your magnitude is the basically like the distance between, let's say it goes like that. Your magnitude is this value up here, and your frequency is how fast. Okay, but let's go over the conversations that we had earlier. I'm gonna switch my screen because I don't know, because I said I'm freaking sick. I hope I'm not sick. I really hope I'm not. Okay. But you talk about rockets and how that relates to vectors. So I'm going to search that up really quickly and see if there's something, and then we'll talk about whether or not there are more dimensions. And then I should wrap up the stream because I do need to leave somewhere. I still need to do things, unfortunately. How vectors relate to rockets in physics applications. Okay. So, forces. The rest are all... Okay. So, for if my computer loads, my freaking computer loads, it says forces which operate a rocket in flight, so like weight, thrust, and aerodynamic forces, they are all vector quantities, meaning that they have like more than one type of quantity. In this case, when we're talking about displacement, we use like the distance and the direction, but there are still like ways, like all these forces sometimes will have two components, but that doesn't necessarily mean that they have the displacement component. And why isn't my thing working? But yeah, basically vectors are very crucial parts of explaining forces, motions, weight, thrust, and aerodynamic stuff that I don't know. And what we learned today is actually how to calculate these vector spaces. It's not necessarily about learning displacement. Oh, is my internet shut? What the heck? It's not necessarily solely to about displacement, but it's more about learning how to operate and manipulate vector values to calculate certain things, such as trajectory, velocity, and acceleration, and thrust as well. Okay. Remember that a life spent failing is more honorable than a life spent doing nothing. That's true. I feel like I'm doing nothing. Barry, hello! Hello, hello! It's unfortunate because I'm just gonna end stream soon. But I guess vector is, it's like a, how do I say this? It's kind of like, it's a specific type of value. A specific sort of form of value that can be used to represent many, many things. So that's what I got from my very quick Google search and looking at NASA's website. But yeah, basically, because certain forces and certain components of calculating, like the movement of a rocket, have multiple, have like two components to them, and in our case, what we learned about was displacement. So we had that magnitude and direction, or like that place and direction. But yes, what we learned is more about the math on how to manipulate the vectors, which I'm assuming later on in this textbook, which I'm pretty sure. But it's quite a few more chapters forward. But if we talk about like acceleration and stuff like that, I'm pretty sure vectors will come in handy, and we'll use the skills that we learned to manipulate the vectors, in this case represented by displacement, to sort of calculate stuff. Such as forces. Basically, vector is basically how things end up in certain place. I guess so. I guess so. It determines the position. Yeah, it's oftentimes used to determine position. It's a good... vectors are a good representation of many forces and how things move. Not only position, but also forces. Yes, exactly. And direction. Sometimes there's like directional of the force, or stuff like that, if I remember correctly. Okay, now the second topic before I have to leave. Are there four-dimensional planes? Dimensional planes. So four-dimensional space. So four-dimensional space does exist. It's a mathematical extension of the concept of three-dimensional space. So I guess so. It's I guess it doesn't exist, like, it's a mathematical concept, I guess. I don't know how that works. I don't know anything, really. But yeah. I wonder if there's fifth dimensional planes. Fifth dimensional is a space with 5 dimensions. So I guess it does. I think it only exists, like, mathematically, though. I don't know how that works. Okay. But yeah. So I guess there are fifth dimensions. It's only mathematical in a space. It's a sequence of numbers that represent a location in a dimensional space. I don't think it exists in real life. But does it exist in math and stuff? Can people make it work? I guess so. So, yeah. I guess it exists in math. Or some people believe it exists in math. You know, sometimes science is like a belief. But I'm not gonna go into that. But, okay, yeah, that's about it. It exists in math, supposedly. Alright, but I'm gonna wrap up here, and... yeah, I'm gonna raid someone, so if you're new to the channel, hello, welcome. I'm Blueberry. I call myself a failed engineer. I saw that you said I should switch it to potential engineer, but I think it's funnier if I call myself a failed engineer. But usually at the end of my streams, I always raid someone, because unfortunately I can't raid someone on YouTube as easily as I can on Twitch. I do it on Twitch. If you would like to join us, feel free to, but if you don't want to, or if you can't, or for any reason, please never ever feel pressured to raid with us. I have a raid message. That's my raid message, and I will find someone to raid. Let's see if someone is on. I don't think any of my friends are on. And I always put the link, by the way. I put the link in the chat. Sky is on! Okay, my friend is on! Sky! She's doing tarot readings. I love her tarot readings. They're like super relaxing. Great as like just to have listen to her. But she's super nice. If you do say hello, please be nice to her. Give her a warm welcome. We will raid her in a few seconds. Let me switch to my stream ending screen. Okay, let me set it up. We will raid in 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. Beep boop. Bye everyone. Bye bye.